We are going to start Unit 3 AC Power Analysis. In this unit, there are mainly 4 topics: instantaneous power, average power, apparent power and power factor, and last, complex power. Since these power topics are with reference to AC circuit, first we need a clarity on the term phase and phase difference. So first we will try to understand what is phase and phase difference and their significance in 3 different circuits like a pure resistive circuit, inductive circuits and capacitive circuit. After that we will continue with our main topics, different kinds of power. Let's have a look at this animation where we have an AC voltage source and a single resistance. So this type of circuit is referred as a pure resistive circuit where you have only resistance as the element. Now we are trying to plot here a graph with respect to time for the voltage supplied as well as the current flowing to the resistance. So when you start this animation, you can see here 2 graphs, the orange one for representing the voltage and the purple one representing the current. Now these 2 waveforms for the voltage and the current are called to be in phase. So what is meant by in phase? You can see here the waves are starting at the same point and ending at the same point. Or in other words, if the maximum of the 2 graphs coincide or at the same point and the minimum of the 2 graphs also is at the same point, then those 2 waves or the graphs are called to be in phase. So the summary is the voltage signal and the current signal in such an example don't have any phase difference. Or if you represent the voltage by the expression V is equal to Vm sin omega t, the current can be represented by a similar expression Im sin omega t. Please note that in both the expression, the phase or the angle is the same. There is no phase difference. Where Im is just Ohm's law, Vm over R. Now let's have a look at an inductive circuit. So here the resistance is replaced by an inductance. So this is a pure inductive circuit. So here again the voltage applied is Vm sin omega t. So let's see what will be the expression for the current flowing through this inductance. For this, let's start the animation. So you can see here the current here is not in phase with the voltage. You can clearly see that there is a phase difference. As it clear here, see the maxima of the voltage is here, but the maxima of the current is here. The minimum of voltage is here, the minimum of the current is here. So obviously there is a phase difference between the voltage signal and the current signal. And in this case, the current is said to be lagging behind the voltage. If you look carefully the voltage signal and the current signal, you can see that there is exactly a phase difference of 90 degree. That is, when the voltage is high at its peak, the current is at 0. So if you represent the voltage and current by equation, V is Vm sin omega t, but the current is Im sin omega t minus 90 degree. This minus 90 degree is the phase difference between the voltage and the current in a purely inductive circuit. The expression for Im is similar to the Ohm's law, but it's not R over here. It's Vm over ZL, where ZL represents the reactance of the inductance. Okay, now let's have a look at a capacitive circuit. So here you have a single capacitor connected. Now look at the animation. So as you observe here, you can find here again there is a phase difference between the voltage and the current. But unlike the previous example, here the current is in front of the voltage, or the current is said to be leading the voltage. So if you try to represent the voltage and the current mathematically, voltage can be represented as V is equal to Vm sin omega t. The current can be represented as Im sin omega t plus 90, and Im is equal to Vm over Zc, where Zc is the reactance due to the capacitive element. So if you have an LCR circuit, the voltage and current relationship can be represented as V is equal to Vm sin omega t and I is equal to Im sin omega t plus phi, where phi is called as the phase difference between voltage and the current. Now in some reference books you can find the expression for the voltage and current by this way, where V is equal to Vm cos omega t plus theta V and I is equal to Im cos omega t plus theta I. Whether it is cos or sine, that represents the sinusoidal nature, and here they have shown that there is an initial phase for the voltage and a phase for the current. So in this case the phase difference will be theta V minus theta I. So with this discussion on phase and phase difference, now we are ready to start with the main content of this chapter. So the first two topics that is covered in this video are the instantaneous power and the average power. Please continue watching the video.
Let's quickly recall a couple of things about an LCR circuit, something that we've already learned earlier. And in case you're not familiar with an LCR circuit, I suggest you first go through the lesson titled LCR in series and then come back to this chapter. Now say a voltage V, which is given by Vm sin omega t, which is an alternating voltage, is applied to this LCR circuit. Now the current I in this case is written as Im sin omega t plus phi, where if you recall, Vm is the voltage amplitude and over here Im is the current amplitude, omega is the angular frequency and phi is the phase. Now if you recall, power is the product of voltage and current. So power is equal to V times I. Now we just wrote the expression for V as Vm sin omega t and I as Im sin omega t plus phi. So we can write the power consumed in an AC circuit, in an LCR circuit, as V times I, which is equal to Vm Im sin omega t times sin omega t plus phi. Now you know that since this value of V and I are the instantaneous value of voltage and current, so this expression for power is also the instantaneous power, which means the power consumed at each instant of the circuit. If you substitute the value of t over here, you get the value of power which is consumed at that point of time. Okay, now I want you to be ready for a lot of mathematical steps. The power P is equal to Vm sin omega t times Im sin omega t plus phi. Now we need to find the average value of power. So to find out the average value of power, we find out, so we'll use the trigonometric identity 2 sin A sin B is equal to cos A minus B minus cos A plus B. So we use this trigonometric identity and we write power as Vm Im, and if you look at we combine these two terms together and write this as cos phi minus cos 2 omega t plus phi, where we've taken omega t as A and omega t plus phi as B and put this into this formula. So what we are looking at is the average power, and which means the average of this entire term that we've got over here. Now what we need is the average of the first term, and the first term would mean Vm Im cos phi minus the average of the second term, which is cosine 2 omega t plus phi. So this term you can see is a constant because Vm is a constant, Im is a constant, and the phase phi is a constant value. So the average of this term will be Vm Im cos phi, and the average of the second term, since this is a cos theta type of a term, the average of this term will turn out to be 0. See, you can show this using a graph. Say we draw a graph for a cos function, you get a graph which looks like this, and this would be time 0, and this again is time t. This is a full time period. Now over a full time period you can see that the graph has a positive value. The area, you can see that the area under the graph, which is positive and which is negative, are equal. So the average value of a cos theta term is also, just as a sin theta term, is 0. So we finally get the average power P equals Vm. Let me just write this once again. We had Vm Im cos phi, and splitting 2, we can write this as over root 2 times Im over root 2 times cos phi, so which finally gives us V RMS times I RMS times cos phi. And in case you're not familiar with RMS values, please go through the lesson titled RMS values, and once you've done that, then you can come back to this lesson.